There is a strange and quiet idea at the heart of modern physics, an idea so peculiar that for a long time no one quite believed it could be true. The idea is this: every particle of matter in the universe has a twin, a mirror version of itself. Identical in mass, identical in spin, identical in nearly every measurable way, and yet, in some essential sense, opposite. If the two should ever meet, both will vanish. They will not break apart, or shatter, or scatter. They will simply cease to exist as particles, and in their place, there will be a tiny flash of light. Two photons, traveling away from each other in opposite directions, carry away the energy that the particles once had. This is antimatter, and tonight, we are going to spend a long while with it. There is no urgency to this. Nothing here that needs to be hurried. We will move slowly through the strange history of how antimatter was first imagined, then how it was found, then how it was made, captured, and studied. We will drift through the quiet laboratories where physicists keep a few hundred antiparticles suspended in fields of invisible force. And we will go further out, to the galactic center, where clouds of these particles annihilate each other in soft showers of gamma rays. We will sit for a while with the deepest unanswered question of cosmology, which is why the universe is made of matter at all, and not of nothing. And we will end, as all such journeys end, in a kind of quiet that is older than the questions. So settle in. There is nowhere to be. The universe is in no hurry, and antimatter, for all its strangeness, is patient enough to wait for us. Our story begins, as so many stories in modern physics do, with an equation, a single mathematical sentence written on a piece of paper in Cambridge, England, in the year 1928. The man who wrote it was named Paul Dirac. He was 25 years old. He was, by all accounts, one of the strangest people who ever did physics, which is saying something. He spoke rarely. He answered questions in single sentences when he answered them at all. His colleagues invented a unit of conversation, the Dirac, which corresponded to 1 word per hour. He sat in his rooms and worked, and the work he did was so deep and so beautiful that some of his contemporaries compared him to Newton. Dirac was trying to do something that seemed, at first, like a small technical problem. Quantum mechanics had just been invented. The Schrödinger equation, written only a year or two earlier, described how electrons moved and behaved at the atomic scale, and it worked beautifully. But it had a flaw. It was not relativistic. It did not take into account the lessons of Einstein's special theory of relativity, which said that any object moving fast enough must be described by laws that respect the speed of light as the universal limit. Electrons, it turned out, often move very fast. The Schrödinger equation could not properly describe them at those speeds. Dirac set himself the task of writing down a version of the quantum equation that would also be relativistic. It was a hard problem. Others had tried and failed, or tried and produced something that gave nonsensical answers. Dirac approached it the way he approached everything, slowly, alone, with the quiet faith that the right mathematical form would, if he found it, simply work. And then he found it. The Dirac equation. A short, elegant expression written in the formal language of physics that married quantum mechanics to special relativity for the first time. It described the electron with extraordinary precision. It predicted properties of the electron, like its spin, that had been measured but not yet understood. It was, by any measure, a triumph, but it had a strange feature. The equation, when you solved it, gave 2 sets of answers. One set described the electron as expected. The other set described something else. Something with the same mass as the electron, the same spin, but with the opposite electric charge. A positive electron, in other words. a mirror version. At first, Dirac did not know what to make of this. He tried for a while to suggest that perhaps these solutions described the proton, the other charged particle known at the time. But the proton was nearly 2,000 times heavier than the electron, and the equation insisted that whatever this mirror particle was, it must have exactly the electron's mass. So that interpretation could not work. For a few years, Dirac and the other physicists of his generation puzzled over what to do with these extra solutions. Some wanted to discard them, to declare them mathematical artifacts that had no physical meaning. But Dirac, slowly, came to a different conclusion. The mathematics, he believed, was telling him something true. The equation was describing a particle that no one had ever seen, a particle that, according to all the chemistry and biology of the world as understood at the time, had no reason to exist. And yet there it was, waiting in the symbols. In 1931, Dirac quietly suggested in a published paper that the equation might be describing a new kind of matter, a positive electron. He called it, tentatively, an anti-electron. He suggested that for every kind of particle in the universe, there might be a corresponding antiparticle, identical, except for opposite charge. He suggested that the universe might be more symmetrical than anyone had supposed. And then he went back to his quiet work and waited to see if anyone would find one. He did not have to wait long. In Pasadena, California, at the California Institute of Technology, a young experimentalist named Carl Anderson was working in a basement laboratory. He was 26 years old, only slightly younger than Dirac, and he was studying something called cosmic rays, the streams of high-energy particles that fall from the sky onto the Earth at all hours of the day and night. Cosmic rays had been discovered around 1912 by Victor Hess, who had flown a balloon into the upper atmosphere and noticed that his radiation detectors clicked more often the higher he went. The radiation was coming from above, from beyond the atmosphere, from somewhere out in space. By the early 1930s, cosmic rays were a hot topic. No one was quite sure what they were made of. They were known to be charged particles of very high energy, but their composition was a mystery. Anderson, working under his mentor Robert Millikan, had built an instrument to study them. It was called a cloud chamber. The principle was simple. A glass cylinder was filled with vapor, supersaturated, so that any charged particle passing through would leave a trail of tiny droplets behind it, the same way a jet airplane leaves a contrail across the sky. By photographing those trails, Anderson could see, in effect, the tracks of individual particles. By placing the cloud chamber inside a powerful magnet, he could see those tracks curve, because charged particles curve in magnetic fields. The direction and tightness of the curve told him about the particle's charge and mass. For a long time, the tracks Anderson saw were the tracks he expected. Most of them belonged to electrons, curving in the way negative particles ought to curve. Some belonged to other particles, heavier, more sluggish. But every so often, he saw a track that puzzled him. A track that had the gentle, easy curve of an electron that suggested a particle as light as an electron, but that curved in the wrong direction, as if it were positively charged. At first, he was not sure what to make of these. He wondered if perhaps he was seeing electrons moving in the opposite direction, from below the chamber upward, and being deflected one way when he thought they were going another. To settle the question, he made a small but elegant modification. He placed a thin plate of lead across the middle of the cloud chamber. A particle passing through the lead would lose some of its energy, and after passing through, it would curve more tightly than before. By looking at the change in curvature, he could tell, unambiguously which direction the particle had been traveling. On the evening of August 2nd, 1932, Anderson developed a photographic plate that showed exactly such a track. A particle had entered the cloud chamber from below, passed through the lead plate, slowed down on the other side, and curved more tightly as it continued upward. The mass was that of an electron. The direction of the curve told him unmistakably that the charge was positive. He stared at it for a long time. He did not know at the time that Dirac had predicted such a particle. The two men had been working in different countries on different problems, and the connection between Dirac's equation and Anderson's photograph would be made only later. But Anderson had his discovery. A positive electron. He gave it a name, positron. The paper in which he announced the discovery was published the following year, with the curiously cautious title, The Apparent Existence of Easily Deflectable Positives. Within months, other experimentalists in other laboratories had confirmed his finding, and the connection to Dirac's equation became clear. The first piece of antimatter had been seen. Anderson would later say that the discovery was, in his words, wholly accidental. He had not been looking for antimatter. He had been studying cosmic rays. The positron had simply walked into his cloud chamber and announced itself. He won the Nobel Prize for it in 1936. Dirac had received his own Nobel 3 years earlier, in 1933, for the equation that had foretold what Anderson would later see. It is worth pausing here for a moment, because what happened in those 4 years, between 1928 and 1932, was a quietly extraordinary thing. A young man sitting alone in Cambridge, writing equations on paper, had imagined a kind of matter that no one had ever observed. He had insisted, almost against his own initial inclination, that the mathematics meant what it said. And then, a few years later and most of the way across the world, another young man, in another quiet room, had pointed a camera at the sky and photographed exactly the particle Dirac had described, without ever speaking to each other, without coordinating. The universe had been waiting with one of its hidden symmetries for someone to notice, and two people almost simultaneously had noticed. For a long time after that, the positron was the only known piece of antimatter. It was understood to exist. It was occasionally observed in cosmic rays. But the rest of the antimatter family remained a theoretical promise. If Dirac's equation was right and the symmetry was real, then there ought to be antiprotons too, and antineutrons, and every other kind of antiparticle, one for every kind of particle. To make these heavier antiparticles, however, would require energies far beyond what any laboratory in the 1930s could produce. The positron is light, the equivalent in mass of about 1/2000 of a proton. Cosmic rays could easily carry enough energy to produce one. But to make an antiproton would take roughly 2,000 times more energy, and there was, for many years, no machine on Earth capable of providing it, so the universe waited again. The positron sat alone in the catalog of antimatter for more than 2 decades. The rest of the antimatter family was assumed, but unseen. The wait ended in 1955 in Berkeley, California, on the western edge of the United States. There, on a low hill above the bay, an enormous new machine had just been completed. It was called the Bevatron. The name came from the unit of energy it could deliver, billions of electron volts, abbreviated BV in those days. The Bevatron was a proton synchrotron, a circular accelerator that could whip protons around a ring until they reached very nearly the speed of light, and then crash them into a target. It was, when it was switched on in 1954, the most powerful particle accelerator in the world. The Bevatron had been designed, in part, with the antiproton in mind. The physicists who designed it knew that to make an antiproton, you needed enough energy in a collision to produce both a proton and an antiproton at the same time. The reason is a conservation law. You cannot, in our universe, create antimatter alone. Antiparticles can only be created in pairs with their corresponding particles, balanced like the two sides of an accounting ledger. To make one antiproton, you must make one proton along with it. To make one positron, you must make one electron. The total amount of what physicists call baryon number, or lepton number, has to be preserved. So to make an antiproton out of pure energy, you need enough energy to make both an antiproton and a proton, which together is about 2,000 times the mass energy of a single electron, and that means about 6 billion electron volts, give or take. The Bevatron could just barely reach those energies, and it had been built, in part, expressly for this purpose. The team that set out to find the antiproton was led by two men, Emilio Seger and Owen Chamberlain, working with two collaborators named Clyde Wiegand and Thomas Ypsilantis. They began their experiments in the first week of August, 1955. Their plan was straightforward in concept and fiendishly difficult in practice. They would direct the Bevatron's high-energy proton beam at a copper target, some small fraction of the collisions inside that target ought to produce antiproton-proton pairs. They would then sift through all of the particles that came out of the target, looking for the ones with the right combination of properties: negative charge, proton mass, the signature of an antiproton. The trouble was that for every antiproton produced in the target, there would be hundreds of thousands of other negatively charged particles, mostly pions, that looked superficially similar. To find the antiprotons, the team had to measure each particle's velocity and momentum with great precision, and from those two numbers calculate its mass. Only the particles with proton mass would be antiprotons. Everything else would be a contaminant. They built an apparatus that included velocity-selecting detectors, magnets to measure momentum, and an array of counters arranged so that only particles with exactly the right properties would trigger a signal. They started the run on August 25th. After a few days of tuning, they began to see signals. About one antiproton for every few 100,000 other particles passing through. By early October, they were confident enough to write to the journal Physical Review. The paper, titled simply Observation of Antiprotons, was received 8 days after submission and published on the 1st of November, 1955. Seger and Chamberlain shared the Nobel Prize in Physics for this in 1959. 27 years after Dirac's equation had first hinted that the universe might be symmetrical, the second piece of antimatter had finally been made and seen. The antineutron followed a few months later. In 1956, a team at the same laboratory, led by Bruce Cork along with Glenn Lambertson, Orst Piccioni, and William Wenzel, produced antineutrons in the Bevatron as well. The antineutron is a curious thing. Like the neutron, it carries no electric charge, so you cannot tell it apart from a neutron by simply watching it bend in a magnetic field. They are not magnetic mirror images in any obvious sense. The way you distinguish an antineutron from a neutron is by what happens when it meets ordinary matter. The antineutron annihilates with the protons and neutrons in a target, producing a characteristic shower of particles. The neutron simply scatters. Once you know what to look for, the difference is clear. By 1956, the catalog of antimatter included the positron, the antiproton, and the antineutron, enough in principle to build an entire mirror version of ordinary atomic matter. Whether anyone would actually build such a mirror matter was, at the time, a question for the distant future. To produce a positron is one thing, producing an antiproton is harder. To make an actual atom of antimatter, an antiproton bound to a positron, behaving the way ordinary hydrogen does, would require not just energy, but precision. You would need to cool the antiparticles down. You would need to bring them together gently enough that they could combine into a stable system. And you would need to hold the resulting antiatom away from any contact with ordinary matter, because the moment such contact occurred, the antiatom would vanish in a flash of gamma rays. It would take another 40 years before anyone managed it. But before we follow that thread, let us pause for a while in the strange territory that the discovery of these antiparticles had opened up, because by the late 1950s, the existence of antimatter had ceased to be controversial. It was, by then, simply a fact of nature. And like all facts of nature, once accepted, it began to raise questions that were harder than the discovery itself. The first and most obvious question was this: if the universe is symmetrical, if matter and antimatter are mirror twins of one another, then why is the universe made almost entirely of one and not the other? The Earth is made of ordinary matter. The Sun is made of ordinary matter. The planets, the stars, the galaxies, as far as we can see, are made of ordinary matter. Antimatter exists, but only in trace amounts. It appears in cosmic rays. It appears in the decay of certain radioactive isotopes. It appears in laboratories when we make it. But it does not, anywhere we can see, make up significant chunks of the cosmos. There are no antimatter planets, no antimatter stars, no antimatter galaxies as far as we can tell. This is strange, because if you trace the universe back to its earliest moments, to the hot, dense state physicists call the Big Bang, you find that energy and matter were freely interchangeable. The temperatures were so high, the conditions so extreme, that pure energy was constantly converting into particle-antiparticle pairs, and those pairs were constantly annihilating back into pure energy. The universe at that time should have produced equal amounts of matter and antimatter. The symmetry of the laws of physics demanded it, and yet here we are, in a universe of matter, in bodies made of matter, sitting on planets made of matter, looking up at stars made of matter. The antimatter has, somehow, gone, or it never came in the same quantities. The asymmetry is so striking and so quietly catastrophic for the simple picture that it has a name: the baryon asymmetry problem, the matter-antimatter asymmetry of the universe. It is one of the great unsolved questions of cosmology. The numbers, when you work them out, are sobering. If matter and antimatter had been created in exactly equal amounts at the Big Bang, then as the universe cooled, every particle of matter would have eventually found an antiparticle to annihilate with. The end result would have been a universe made entirely of light. Photons, traveling in all directions, with no matter left over to form stars, planets, or anything else. The fact that there is anything at all suggests that the symmetry was, very slightly, broken. For every billion or so antiparticles created in the early universe, there must have been 1,000,000,001 particles. The slight excess survived, the rest annihilated, and the universe we live in today is built from that thin, billion-to-one residue. Every atom in your body is, in a sense, a leftover, a particle that happened to find no antiparticle partner to vanish with. How this slight excess came about is the question. We do not, at present, know the answer. We have ideas. The most famous of them was proposed in 1967 by a Soviet physicist named Andrei Sakharov. Sakharov was, like Dirac, an extraordinary mind. He had been one of the principal architects of the Soviet hydrogen bomb. He later became one of the most prominent dissidents of the Soviet era, a Nobel Peace Prize winner, and was exiled to a small city in the heart of Russia for criticizing his own government. In between those two phases of his life, he wrote a short paper laying out the conditions that any physical theory would need to satisfy in order to explain why the universe is made of matter rather than nothing. There are three of these conditions, now known as the Sakharov conditions. The first is that there must be processes in nature that can change the number of matter particles, the total amount of baryon number, the count of protons and neutrons, and similar particles must not be perfectly conserved. There must be some loophole, some way that the universe can, very rarely, produce or destroy baryons without producing or destroying their antimatter partners. The second condition is that the laws of physics must distinguish, at some deep level, between matter and antimatter. Not just in the label, but in actual behavior. The symmetry called C, charge conjugation, which exchanges every particle for its antiparticle, must be violated, and the combined symmetry called CP, which exchanges particles for their antiparticles and also reflects them in a mirror, must also be violated. Without these violations, any process that produces extra matter would be balanced by an equivalent process that produces extra antimatter, and no net asymmetry could arise. The third condition is that the universe must, at the relevant time, be out of thermal equilibrium. If everything is in a steady state, with each process balanced by its reverse, then any small asymmetries that try to emerge will be washed away. There has to be a moment in the universe's history, an expansion or a phase transition, that allows the asymmetry to be locked in before it can be undone. All three of these conditions, Sakharov argued, must be met for the universe we see to have come about, and he pointed out, with characteristic insight, that we already knew one of them to be true. The CP symmetry had been shown, just 3 years earlier, to be violated. The discovery had come from a strange, almost accidental experiment at Brookhaven National Laboratory in New York. There is something worth pausing on here, in the figure of Sakharov himself. He had been, as we mentioned, one of the lead designers of the Soviet thermonuclear bomb. By the late 1950s and into the 1960s, he had begun to turn his attention to questions both political and cosmological. The same mind that had calculated the conditions inside a fusion reaction had begun to consider the conditions inside the early universe, and at the same time had begun to question the moral foundations of the state he had served. The paper proposing the 3 conditions for baryogenesis was published in 1967 in the Soviet physics journal JETP Letters. It was a short paper. It made a strikingly simple argument. It opened a door that has remained open ever since. A few years later, Sakharov would write his more famous essay calling for intellectual freedom and disarmament. He would lose his security clearances. He would eventually be exiled to the city of Gorky. He would, in time, win the Nobel Peace Prize for his human rights work, though he could not travel to accept it. His scientific paper, written in the middle of all this, asking the question of why the universe contains matter rather than nothing, has outlasted the political conditions in which it was written. The question remains. The answer is still being sought. The story of CP violation begins, like so many physics stories, with an experiment that was expected to confirm something. It ended up doing the opposite. In 1964, two physicists named James Cronin and Val Fitch, along with their collaborators, were studying a particle called the neutral kaon. Kaons are a kind of meson, a class of particle made of a quark and an antiquark. The neutral kaon is unusual in that it can oscillate between being a kaon and being its own antiparticle, the antikaon, in a quantum dance that has fascinated physicists ever since. Cronin and Fitch were not, in their own description, looking for anything revolutionary. They expected the neutral kaon to obey CP symmetry. They expected, in other words, that whenever the kaon decayed into other particles, the pattern of those decays would be symmetric between matter and antimatter. This was the firm prediction. CP symmetry was, at the time, considered one of the deepest principles of physics. Lev Landau, only a few years earlier, had argued that CP symmetry was the truer symmetry of nature, the real reflection of the deep mathematical structure that distinguished particles from their antiparticles. But when Cronin and Fitch looked at their data, they found something they had not expected. About 1 in 500 neutral kaon decays produced a pattern that CP symmetry forbade. The number was small. The effect was subtle, but it was real, and it was unambiguous. The symmetry was broken. Nature, in this tiny corner of the subatomic world, distinguished between matter and antimatter in a way that no one had thought possible. The discovery was, in its quiet way, devastating to a certain kind of physical intuition. It said that the universe is not perfectly symmetric in the way that the elegant equations had suggested. Somewhere in the laws of physics, there is a small bias, a preference, a slight tilt of the scales between matter and antimatter. Cronin and Fitch received the Nobel Prize for the discovery in 1980. The full meaning of what they had found is still, in many ways, being worked out today. The standard model of particle physics, the great theoretical edifice that describes the matter and forces we know about, contains a place for CP violation. It enters through what is called the CKM matrix, named after three physicists, Kabibo, Kobayashi, and Maskawa, who worked out how the different kinds of quarks mix and transform under the weak nuclear force. The matrix contains a single complex number, a single phase, that breaks CP symmetry in just the way Cronin and Fitch observed. It explains, in great detail, the pattern of CP violations seen in kaons. It also predicted, before it was measured, the pattern of CP violation in heavier mesons made of bottom quarks, which was confirmed in experiments at facilities like SLAC in California and KEK in Japan in the early 2000s. In 2025, the LHCb experiment at CERN announced the first observation of CP violation in baryons, a particularly heavy class of particles. The standard model continues to pass these tests, and yet, when you take the amount of CP violation that the standard model predicts, and you try to use it to explain the baryon asymmetry of the universe, you fall short. By an enormous amount. The CP violation we know about is too small, by many orders of magnitude, to account for the matter-antimatter imbalance we observe. Somewhere, there must be more CP violation, some additional source, some new physics beyond the standard model that we have not yet found. The matter-antimatter asymmetry is, in this sense, a marker, a signpost pointing toward physics we do not yet understand. The universe is telling us, through its own existence, that the rules we have written down so far are incomplete. There are many theories about what the missing piece might be. Some involve a process called leptogenesis, in which heavy, hypothetical particles called right-handed neutrinos decay in the very early universe in slightly different ways for matter and antimatter. producing an excess of leptons, which is then converted into an excess of baryons by other processes. Some involve supersymmetry, an extension of the standard model in which every known particle has a heavier partner, and the partners introduce new sources of CP violation. Some involve grand unified theories, in which the strong and weak forces merge at extremely high energies and new processes become possible. None of these has yet been confirmed. Each is a candidate. Each waits patiently for the experiment to tell us whether it is right. In the meantime, the question remains open. Why is the universe made of matter? We have inherited a world that should not, by the simplest accounting, exist. We are made of leftovers. The matter we see, the matter we are, is the residue of an enormous original symmetry that was broken, very slightly, at the very beginning. In a way we cannot yet fully explain. It is, in its way, a comforting thought. The universe is not done revealing itself. There is more to know. And the things we are made of are, in a quiet sense, the result of an ancient and beautiful asymmetry whose origin is still being worked out. Let us drift now to another part of the story, a part that begins not with theory, but with the practical question of what to do with antimatter once you have made some. By the late 1970s, after several decades of producing antiprotons in particle accelerators, physicists had begun to wonder whether they could go further, whether they could not just make antiparticles, but capture them, hold them, and study them at leisure. The trouble with antiparticles, of course, is that they cannot be held in any ordinary container. The moment they touch the walls, they annihilate with the matter of the walls, and they are gone. To store an antiproton, you need a container that is not made of matter at all. A container made of forces, magnetic fields and electric fields, arranged so that the antiproton is suspended in midair, in a vacuum, never touching anything. The device that accomplishes this is called a Penning trap, after the Dutch physicist Frans Michel Penning, who invented an early version in the 1930s for entirely different purposes. A Penning trap consists of a strong magnetic field, oriented along one axis, and a configuration of electrodes that produces a particular shape of electric field. A charged particle placed inside the trap will spiral around the magnetic field lines, held in place by the magnetic force, and will be confined along the axis of the magnetic field by the electric field. The particle, if you tune the fields correctly, can be held in this trap for very long times, for many years in some cases, without ever touching a wall. Penning traps are one of the great quiet technologies of modern physics. They are not as famous as particle accelerators or large telescopes. They do not make headlines often, but they are the patient instruments that have allowed physicists to study antimatter in detail, to compare it to ordinary matter, to ask whether the symmetry between the two is really exact, or whether there are tiny differences that might point the way to new physics. CERN, the European Organization for Nuclear Research, established near Geneva in the 1950s, became the principal home of this kind of antimatter research. Beginning in the late 1980s and early 90s, CERN built a series of dedicated facilities for slowing down antiprotons and storing them in Penning traps. The first was called LEAR, the Low-Energy Antiproton Ring. The second, opened in 2000, was called the Antiproton Decelerator, or AD. The most recent addition, called ELENA, opened in 2017 and is capable of slowing antiprotons to even lower energies, suitable for the most precise experiments. The principle of these facilities is simple in concept. Antiprotons are produced, as they always have been, by smashing protons into a target at high energies. These antiprotons come out of the target moving at nearly the speed of light. They are then captured magnetically and circulated around a ring, where their energy is gradually reduced by various cooling techniques. Eventually, they are moving slowly enough to be loaded into penning traps and studied. The whole process is exquisitely difficult. The yield is poor. For every billion or so collisions, you might get a handful of useful antiprotons. But it works. In 1995, using LIR, a team of physicists at CERN led by Walter Oehlert announced something that had been 30 years in coming. They had produced the first atoms of antihydrogen. Antihydrogen is the antimatter equivalent of hydrogen, the simplest atom in the universe. A hydrogen atom consists of a proton with an electron orbiting around it. An antihydrogen atom consists of an antiproton with a positron orbiting around it. The same structure, just mirrored. The Oehlert team had managed to produce 9 such atoms by directing antiprotons through a stream of heavy atoms in such a way that, very occasionally, an antiproton would pick up a positron from the cloud of electron-positron pairs created near the heavy nuclei. The 9 atoms existed for about 40 billionths of a second each before they encountered ordinary matter and annihilated. But they had existed. The first complete pieces of antiatomic matter had been made. For a few years after that, the technique was refined. By 2002, 2 experiments at the antiproton decelerator, named Athena and ATRAP, had succeeded in producing antihydrogen in much larger quantities. They were also able to produce it cold, at very low temperatures, by combining clouds of antiprotons with clouds of positrons in carefully designed traps. The antihydrogen atoms produced by these methods were neutral, of course, because they had no net charge. Neutral atoms cannot be held in a penning trap, which relies on electric fields that only affect charged particles. So the antihydrogen atoms, once formed, drifted off and annihilated quickly. The next step was to hold neutral antihydrogen. To do this, physicists exploited a subtler property of atoms. Even though an atom has no net charge, it does have a magnetic moment, a kind of tiny internal magnetism, and that magnetic moment will respond weakly to a magnetic field by creating a region of space where the magnetic field has a minimum, surrounded by regions of stronger field. You can build a trap that holds neutral atoms whose magnetic moments are oriented in the right direction. The atoms slide toward the minimum field, like marbles rolling into a bowl, and they sit there. This is what the ALPHA experiment at CERN accomplished, beginning around 2010. The ALPHA collaboration, an international team of physicists, succeeded in trapping antihydrogen atoms for about 1/10 of a second. The result was reported in the journal Nature in November of 2010. Within a few years, the trapping times had been extended to many minutes. Eventually, the experiment was holding antihydrogen for over 15 minutes at a time, with hundreds of atoms confined simultaneously. A separate experiment, called BASE, has succeeded in storing antiprotons in a penning trap for over 14 months without losing them, the longest period of antimatter storage ever achieved. These long storage times have opened a new era of antimatter physics. Once you can hold antihydrogen, you can study it. You can shine lasers on it and measure how it absorbs light. You can compare its energy levels with those of ordinary hydrogen, which have been measured to staggering precision over the past century. And you can ask whether, in any detail, antihydrogen behaves differently from hydrogen. Because if the symmetry between matter and antimatter is exact, the energy levels of antihydrogen ought to be identical to those of hydrogen, down to many decimal places. Any tiny difference would be a signal of new physics, a crack in the foundations. So far, no such cracks have been found. The transitions in antihydrogen, measured by the ALPHA experiment beginning in 2016, agree with the predictions for hydrogen to extraordinary precision. The charge of the antiproton, measured by the BASE experiment, agrees with the charge of the proton to better than 1 part in a billion. The mass of the antiproton, divided by its charge, agrees with the corresponding ratio for the proton to better than 1 part in 10 billion. The magnetic moments of the proton and antiproton have been compared. The antiproton's lifetime, if it has a lifetime, must be longer than about 1/10 of a year, which is to say, very long indeed. Everywhere physicists have looked, antimatter has obeyed the predictions. The mirror seems perfect, at least to the precision we can currently measure. But the precision keeps improving, and one day, perhaps, the mirror will reveal a small flaw, a tiny asymmetry that points the way to the missing physics of the early universe. There was one further test that, for many years, remained unperformed. The question of gravity. General relativity, Einstein's theory of gravity, treats all forms of mass energy identically. Whether something is matter or antimatter, the theory predicts it should respond to gravity in the same way. Antihydrogen should fall to Earth with the same acceleration as ordinary hydrogen. Antimatter and matter should be equally attracted by gravity. But this had never been directly tested. The reason is simply that antimatter is so hard to make and so hard to hold. To test how it responds to gravity, you would need to make some. Hold it in a way that lets you measure its motion under gravity alone, and watch carefully. None of the conditions had been achievable until very recently. Some physicists, over the years, had speculated that antimatter might actually be repelled by gravity rather than attracted to it. Such anti-gravity would violate general relativity, but it had not been entirely ruled out by experiment. It would have explained, possibly, some features of the matter-antimatter asymmetry. The idea was a minority view, but it was not impossible. In 2023, the ALPHA collaboration at CERN, using a modified version of its trap called AlphaG, performed the first direct measurement of how antihydrogen responds to gravity. The apparatus was a tall, vertically oriented vacuum chamber. Antihydrogen atoms were trapped at one end, held by magnetic fields. Then the magnetic fields were slowly relaxed, and the trapped atoms were allowed to drift. By watching where they ended up annihilating against the walls of the chamber, the experimenters could determine whether the atoms had moved upward, downward, or in some other direction. The result, published in the journal Nature in September of 2023, was clear. Antihydrogen falls. It falls toward the Earth with an acceleration that, within the precision of the measurement, matches that of ordinary matter. The precision was not yet perfect. The measurement determined the gravitational acceleration of antihydrogen to be about 75% that of ordinary matter, with a statistical uncertainty large enough that the two values agree. Future experiments, including with laser-cooled antihydrogen, will improve the precision dramatically. But the basic question has been settled. Antimatter is not gravitationally repulsive. It falls, like everything else. The principle of universal gravitation, sketched out by Newton and refined by Einstein, holds true even for matter that is, in a sense, the opposite of ordinary matter. There is something quietly satisfying about this result, even though it was, for most physicists, the expected outcome. It says that one of the deepest principles of physics, the equivalence principle, which states that all forms of matter respond to gravity in the same way, applies even at the boundary between matter and antimatter. The universe, in its strangeness, is at least consistent with itself in this one respect. Let us drift away from the laboratories for a while and look upward, because antimatter is not only made in particle accelerators. The universe makes its own antimatter all the time, in places we can see if we know where to look. The most familiar of these places is, in a sense, the human body. Every banana contains a small amount of a radioactive isotope of potassium, called potassium-40. When potassium-40 decays, in a process called beta plus decay, it occasionally emits a positron. The positron flies out of the banana and, within a very short distance, encounters an electron, and they annihilate. A pair of gamma-ray photons goes off in opposite directions. This happens in any given banana roughly once every 75 minutes or so. The amount of antimatter produced is unimaginably small, but it is being produced all the time in fruit bowls and grocery stores all over the world. The same potassium-40 is in our bodies, in the muscles and bones of every person. We are, in a small way, sources of antimatter ourselves. We emit positrons. They do not get far. They find an electron almost immediately, and they vanish. This process of beta plus decay, in which a proton inside a nucleus converts itself into a neutron and ejects a positron, is one of the basic forms of radioactive decay. It happens in many isotopes. Some of these isotopes are used in medicine in a technique called positron emission tomography or PET scanning. The technique works as follows. A patient is given an injection of a substance that has been labeled with a positron-emitting isotope, often fluorine-18, which decays with a half-life of about 110 minutes. The substance is designed to gather in particular tissues of the body. The most common version is a glucose-like molecule called fluorodeoxyglucose, which behaves enough like sugar that the cells of the body take it up readily, especially cells that are using a lot of energy, like cancer cells. Once inside the body, the labeled molecules begin to decay. Each decay emits a positron. The positron travels a short distance, less than a millimeter typically, and then encounters an electron, and they annihilate. Two gamma-ray photons fly off in exactly opposite directions, each carrying 511,000 electron volts of energy, which is exactly the rest mass energy of an electron. The PET scanner consists of a ring of detectors arranged around the patient. When two detectors on opposite sides of the ring register a gamma-ray photon at the same instant, the scanner knows that a positron-electron annihilation has just occurred somewhere along the line between those two detectors. By recording millions of such events and reconstructing where the annihilations happened, the scanner can build up a three-dimensional image of where the labeled molecules accumulated in the body. The image shows, in effect, a map of metabolic activity. It can reveal cancers long before they would be visible to other imaging techniques. It can show how the brain is functioning, how the heart is using energy, and how a drug is being distributed through the body. Antimatter, in this case, is a quiet medical tool. Hospitals around the world perform millions of PET scans every year. Each scan involves the production and annihilation of countless positrons inside a human body. The amount of antimatter involved in any single scan is small, on the order of nanograms, but the effect is real and useful. Antimatter, the strange theoretical curiosity of the 1930s, has become a routine instrument of modern medicine. The 511,000 electron-volt gamma ray, the signature of electron-positron annihilation, is one of the most carefully measured radiations in clinical practice, outside of medicine, and outside of the carefully controlled environment of particle accelerators, antimatter is produced naturally in a variety of places. Cosmic rays, those high-energy particles falling onto Earth from space, contain a small fraction of antimatter. About 1 in 10,000 cosmic ray particles is an antiproton. These are not, as far as we can tell, primordial antiprotons left over from the Big Bang. They appear to be secondary particles, produced when high-energy cosmic ray protons collide with the atoms of the interstellar medium and create antiproton-proton pairs. The ratio of antiprotons to protons in cosmic rays is roughly what you would expect from this kind of secondary production. The Alpha Magnetic Spectrometer, an experiment mounted on the International Space Station, has been measuring cosmic rays since 2011. It has reported the presence of cosmic ray positrons in numbers that exceed simple secondary production at higher energies, hinting that there may be additional sources of cosmic positrons, possibly nearby pulsars, possibly something more exotic. The data continue to be analyzed. The instrument has searched for cosmic ray antihelium, which would be a striking signal of primordial antimatter, since antihelium is hard to produce in secondary collisions. So far, no antihelium has been definitively found. Lightning storms on Earth, it turns out, produce small amounts of antimatter. The strong electric fields in thunderclouds can accelerate electrons to relativistic speeds, and when those electrons crash into atoms in the atmosphere, they sometimes produce gamma rays of enough energy to make positrons. NASA's Fermi Gamma Ray Space Telescope, looking down at the Earth's atmosphere, has occasionally seen bursts of 511 keV gamma rays, the unmistakable signature of positron annihilation, coming from terrestrial thunderstorms. The amount of antimatter produced in any single storm is small, but the universe, it seems, is generous with antimatter in surprising places. And then there is the center of our galaxy. The Milky Way, our home galaxy, has at its center a region of extraordinary activity. There is a supermassive black hole there, called Sagittarius A star, with a mass roughly 4 million times that of the Sun. Around it, the inner region of the galaxy is dense with stars, gas, dust, and various forms of high-energy phenomena. And from this region, gamma-ray telescopes have detected a striking signal, a bright emission line at exactly 511,000 electron volts, the signature of electron-positron annihilation. The signal was first detected in the late 1960s by balloon-borne instruments. Subsequent satellite missions, including the European Space Agency's Integral Observatory, launched in 2002, have mapped the emission in detail. The 511 keV glow comes from a roughly spherical region around the galactic center, with a somewhat asymmetric distribution along the disk of the galaxy. 20 years of integral data, processed and reanalyzed in 2025, have produced the most detailed map of this antimatter annihilation signal yet made. What it shows is that, somewhere in the inner galaxy, positrons are being produced and then slowing down and finding electrons to annihilate with, at a rate of perhaps 10 to the power of 43 positrons per second. This is, by laboratory standards, an enormous amount of antimatter. By cosmic standards, it is small, almost a trace, but it is there. The center of our galaxy is, in some quiet way, an antimatter factory. Where the positrons come from is not entirely settled. Several possibilities have been proposed. One is that they come from a particular kind of radioactive isotope produced in stellar explosions. Type 1a supernovae, in particular, produce large amounts of nickel-56, which decays to cobalt-56, which decays in part by emitting positrons. Over the history of the galaxy, these stellar deaths could have populated the inner galaxy with positrons. Another possibility is that the positrons come from compact objects, binary star systems in which one of the stars is a neutron star or a black hole, and the other is an ordinary star whose material is being slowly drawn off and consumed. Such systems are known to emit gamma rays, and they could plausibly be producing positrons in their accretion flows. The asymmetric distribution of the annihilation signal along the galactic disk seems, at least in some analyses, to follow the distribution of these compact binaries. A third possibility is more speculative. Some theorists have proposed that the positrons might come from the decay of dark matter particles, the mysterious substance that makes up about a quarter of the universe's mass-energy budget, but whose nature remains unknown. If dark matter consists of particles that decay very slowly into electron-positron pairs, this could explain part of the signal. Other theories invoke primordial black holes, hypothetical small black holes formed in the early universe, which might convert protons into positrons through quantum processes. None of these explanations is yet established. The 511 keV emission from the galactic center remains one of the more intriguing mysteries in high-energy astrophysics. What is certain is that, somewhere in the inner Milky Way, antimatter is being produced and destroyed continuously. The rate is high enough that, if you could collect it all, the antimatter being created in our galaxy each year would be many kilograms. By comparison, the total amount of antimatter ever produced by human technology is on the order of nanograms. The universe makes antimatter at scales that vastly exceed our own laboratories, and it does so quietly, far from any observers, in regions whose only message to us is a faint gamma-ray glow. Let us pause here a moment, because this is the sort of fact that bears sitting with. There is a region in the heart of our galaxy where, at this moment, electrons and positrons are finding each other and vanishing into pure light. The light has been traveling for thousands of years to reach our detectors. The annihilations were happening when ancient civilizations were rising on Earth, when the pyramids were being built, when there was no one yet alive who would ever hear this said. They were happening, in fact, long before any of these things, all the way back, continuously, for as long as the galaxy has had a center, and they are still happening now, in this moment, photons that we will not detect for thousands of years, yet streaming outward from the inner galaxy. The slow, steady annihilation of matter and antimatter, an enormous and patient process happening without us, in a place we will probably never visit. It is one of the quieter facts about the universe. It does not need us. It does not change because we know about it. It simply happens, has been happening, and will continue happening. Long after every detector we have ever built has rusted away, the slow rain of gamma rays from the galactic center will continue. Let us return now to the laboratories, to the strange technologies by which physicists make and keep antimatter, and the slow improvements that have been accumulating over the past several decades. The basic problem of antimatter, from a practical standpoint, has always been that it is exceedingly hard to make and exceedingly hard to keep. CERN's antimatter decelerator produces, in a typical year, on the order of 10 to the 10 antiprotons, give or take. This sounds like a lot until you do the arithmetic. 10 to the 10 antiprotons have a total mass of roughly 1/10 trillionth of a gram. If you accumulated every antiproton that CERN has ever produced over the entire history of its antimatter program, you would have, in total, a few millionths of a billionth of a gram. The amount is so small that, if it were all annihilated at once with an equal amount of ordinary matter, the total energy released would be enough to light a small bulb for a few seconds. The cost, however, is staggering. To produce a single gram of antimatter, at current rates and current methods, would cost something on the order of trillions of dollars, possibly more. And no facility on Earth comes anywhere close to producing a gram. The largest accumulations of antimatter in laboratories are measured in trapped antiprotons, in numbers ranging from a few thousand to perhaps a million, held for periods of weeks or months in penning traps. By the standards of normal chemistry, these are inconceivably small samples. By the standards of antimatter research, they are luxurious. The reason for the extraordinary cost is the inefficiency of production. When you slam a high-energy proton into a target, the chance that any given collision will produce an antiproton-proton pair, rather than the many other possible outcomes, is small. Of the antiprotons that are produced, only a fraction can be successfully captured and slowed down to useful energies. The rest are lost, either because they are moving too fast in the wrong direction, or because they annihilate before they can be trapped. The whole process, from the proton beam to the trapped antiproton, has an efficiency of perhaps 1 part in a billion or worse. Despite this, the field has made remarkable progress. The first 9 atoms of antihydrogen, produced in 1995, existed for 40 billionths of a second each. By 2002, the Athena and ATRAP experiments were producing tens of thousands of antihydrogen atoms in a single experimental session. By 2010, Alpha was trapping antihydrogen for a tenth of a second. By 2011, the trapping time had been extended to 15 minutes. In recent years, antihydrogen has been held long enough to do laser spectroscopy on it, to measure its energy levels and compare them to those of ordinary hydrogen. The numbers so far agree. The mirror appears at the level of present-day precision to be perfect. There is a smaller, more recent project at CERN that deserves mention here. It is called BASE, the Baryon-Antibaryon Symmetry Experiment. The BASE collaboration has, over the past decade, performed some of the most precise comparisons ever made between protons and antiprotons. They have measured the charge-to-mass ratio of the antiproton to a precision of about 1 part in 70 billion, the most precise such measurement ever made. They have measured the magnetic moment of the antiproton with similar precision. They have, by some metrics, made the most precise measurement of an antimatter property ever achieved, more precise even than the corresponding measurements for ordinary matter. In 2025, the BASE collaboration accomplished something that, for a long time, had been considered very difficult. They built a small, transportable version of their penning trap, called BASE Step. It is, by penning trap standards, compact. It weighs about 1,000 kilograms. It can be loaded onto a truck. It contains a superconducting magnet and a small cooling system that can keep the trap cold for several hours without an external power supply. In early 2025, in a first proof of concept, the team used BASE Step to transport 92 antiprotons across the CERN campus. The first time antimatter had ever been moved from one location to another in this way. The eventual goal is to transport antimatter to laboratories elsewhere in Europe, where measurements can be made under conditions free from the vibrations and electromagnetic noise of the particle accelerator itself. The image is a curious one. A small truck, driving carefully along an ordinary road, carrying inside it a vacuum chamber held at an extraordinary cold, in which a few dozen particles of antimatter spin around magnetic field lines, suspended in fields of force, never touching anything. The amount of antimatter is so small that if the trap failed, the energy released by the annihilation would be negligible. By comparison, the sunlight falling on a single square centimeter of skin in 1 second is roughly 1 billion times greater than the total energy stored in the trap. The transportation is, in this sense, completely safe, but it is also, in another sense, miraculous. A truckload of antiparticles was driven across a small section of Switzerland, the first time that something so contrary to the everyday rules of matter was moved by people from one place to another by ordinary transportation. Let us pause again and consider what antimatter actually is, in a deeper sense than its history alone can tell us, because the modern understanding of antimatter is rooted in a way of thinking about particles that is somewhat strange and worth exploring slowly. In the original Dirac equation, antimatter appeared as a kind of accounting trick. The equation had 2 sets of solutions, and the second set was reinterpreted as a particle with opposite charge. Dirac himself, for a time, proposed an elaborate picture in which the universe is filled with an infinite sea of negative energy electrons, all the states fully occupied, and antimatter appeared as a hole in this sea, a bubble where an electron was missing. The hole, behaving like a positively charged version of the electron, was the positron. This picture, called the Dirac sea, was the working interpretation for a couple of decades. It has since been replaced by something more elegant. The modern picture comes from quantum field theory, which is the framework underlying all modern particle physics. In this picture, what we call a particle is really a localized excitation of an underlying field. There is an electron field that fills all of space. The field can be in various states. The lowest energy state of the field is what we call the vacuum, with no electrons present. The next state, with a little energy added, can contain 1 electron, somewhere in space. The state above that can contain 2 electrons, and so on. The field can also be excited in a different way, with the energy added in the form of a positron rather than an electron. The 2 kinds of excitations are related to each other by a deep symmetry. They are, in a sense, 2 sides of the same field. In this picture, antimatter is not a separate substance. It is a different excitation pattern of the same fields that make ordinary matter. There is one electron-positron field, and electrons and positrons are 2 different kinds of waves on that field. When a positron meets an electron and they annihilate, what happens is that 2 excitations of the field combine and cancel, leaving behind only the photons that carry away their energy. The field returns to its lower energy state. The particles are gone, but the field remains. There is a beautiful and unsettling consequence of this picture, which was pointed out by the Swiss physicist Ernst Stueckelberg in the 1940s and developed further by Richard Feynman. If you look at the mathematics carefully, the equations describing the propagation of a positron look exactly like the equations describing an electron, but with time running in the opposite direction. A positron can be described mathematically as an electron moving backward through time. This is not, most physicists would say, a literal statement about reality. It is a mathematical convenience. It does not mean that positrons remember the future and forget the past. It does not mean that you could send messages backward in time by sending a positron. But the equations work. If you draw a Feynman diagram, one of the small visual aids that physicists used to compute the probabilities of particle interactions. The antimatter lines on the diagram are conventionally drawn with their arrows pointing backward in time. The positron, in this diagrammatic sense, is an electron whose arrow points the wrong way. Feynman once told a story about a phone call he received from his teacher and collaborator, John Archibald Wheeler. Wheeler had been thinking about Feynman's interpretation of antimatter as electrons moving backward through time, and he proposed, half-jokingly, that perhaps there is really only one electron in the universe. It loops back and forth through time, weaving an enormously complicated path. And what we see as the many electrons of the world are actually different intersections of this single electron's world line with our present moment. Each forward-going segment is an electron. Each backward-going segment is a positron. The total number of electrons and positrons in the universe ought, by this account, to be roughly equal, since each forward segment is balanced by a backward one. The fact that we see vastly more electrons than positrons would, in this interpretation, be a kind of accounting problem. The single electron picture is not, to be clear, the modern view. It is more a poetic curiosity than a serious theory. The world contains many electrons. They are excitations of the electron field, and they do not need to be the same particle weaving through history. But the picture is suggestive. It hints at the deep symmetry between matter and antimatter, between forward and backward, between past and future, that lives at the bottom of the mathematics. It hints that the distinction between particle and antiparticle is not as clear in the foundations of physics as it appears in everyday life. One further consequence of the modern picture is worth noting. The annihilation of matter and antimatter is not, properly speaking, a destruction of anything. It is a conversion. Mass becomes energy, in accordance with Einstein's equation, the famous E equals mc squared. The mass energy of the electron and the mass energy of the positron, when they meet, are carried away by two photons, each with an energy of 511,000 electron volts. The energy is conserved. The momentum is conserved. The electric charge is conserved, both being zero. Everything is properly accounted for. What changes is only the form. Two particles of mass become two particles of light. The reverse process is also possible. A sufficiently energetic photon passing near an atomic nucleus can convert into an electron-positron pair. This is called pair production, and it is, in a sense, the time reverse of annihilation. The photon, which carries no mass, gives up some of its energy to produce two particles of matter, one ordinary and one anti, that move off in different directions. Pair production is how cosmic rays produce positrons when they hit the atmosphere. It is also how particle accelerators produce all of the heavier antiparticles. The energy goes in. Particle-antiparticle pairs come out. The accounting is preserved at every step. So matter and antimatter are not different substances, exactly. They are different forms of the same underlying fields, and they can be converted into each other or into pure energy or back, depending on the circumstances. The universe contains many electrons and few positrons, not because the two are made of fundamentally different stuff, but because, very long ago, an asymmetry tipped the balance, and the matter side of the ledger came out slightly ahead. This is, in some sense, the deepest fact about antimatter. It is not, as it sometimes appears in science fiction, an exotic and dangerous substance that exists in its own separate region of the universe, ready to react explosively if it encounters the ordinary kind. It is, instead, a permanent and quiet possibility, woven into the structure of every particle and every field, distinguishable from ordinary matter only by the patterns of its charges and quantum numbers. The universe is, in its bones, more symmetric than it appears. The asymmetry we see is a small wrinkle on a much deeper symmetry that the equations themselves still insist upon. Let us drift now to another aspect of antimatter, which is its appearance in our imaginations. Before antimatter was studied seriously in laboratories, it had begun to appear in the cultural background of the 20th century as a kind of mysterious and powerful substance. It is worth spending a quiet moment on this, not because it is necessarily true to physics, but because it has shaped how many people first encounter the idea. In science fiction, antimatter has appeared as a fuel for starships, as a weapon, as the energy source for warp drives, anti-gravity devices, and various other improbable technologies. The Star Trek franchise, beginning in the 1960s, made antimatter into a household word by featuring it as the power source for the Starship Enterprise. The matter-antimatter reactor of the Enterprise, fictionally, converted antimatter and matter into pure energy, providing the enormous amounts of power needed to drive the ship through interstellar space at speeds faster than light. The science is, of course, fanciful in various ways. Faster-than-light travel is not allowed by special relativity, but the choice of antimatter as the fuel for such a ship was, in its way, a perceptive one. Antimatter is, in fact, the most energy-dense fuel that the laws of physics allow. The annihilation of matter and antimatter converts 100% of the mass energy into other forms, far more than any chemical reaction or nuclear reaction can manage. A kilogram of antimatter, annihilating with a kilogram of matter, would release about 180,000 trillion joules of energy, equivalent to roughly 43 megatons of TNT. By comparison, the most efficient nuclear fusion reaction converts less than 1% of the mass into energy. Antimatter is, in this sense, the ultimate fuel. Various proposals have been made over the years for using antimatter to drive spacecraft. The most discussed is the beamed core antimatter rocket, in which antiprotons annihilate with protons inside the engine, and the charged particles produced by the annihilation are directed by magnetic fields out the back of the ship to produce thrust. Theoretical analyses suggest such a rocket could reach exhaust velocities of perhaps 30 to 40% of the speed of light, making interstellar missions to nearby stars conceivable within a human lifetime. In principle, the practical difficulties, however, are immense. To send a spacecraft to a nearby star using an antimatter rocket would require, depending on the design, anywhere from a few grams to a few thousand kilograms of antimatter. The current production rate at CERN is on the order of nanograms per year. To produce a single gram would require, at the present rate, something like 1 billion years of continuous operation. Even with major improvements in production technology, it is hard to see how the gap could be closed without entirely new approaches. The storage problem is similarly daunting. Modern penning traps can hold perhaps 1 million antiprotons at a time for periods of months. A practical rocket would need to store on the order of 10 to the 20 antiprotons. The traps would have to be scaled up by a factor of 10 to the 14. No one has any idea how to do this with present technology. So antimatter rockets remain, for the time being, a thing of theoretical papers and science fiction stories. They may, one day, become possible. The basic physics is sound. The engineering, however, is so far from current capabilities that any actual antimatter starship is many centuries away at the soonest, and quite possibly forever beyond human reach. For now, the antimatter we make is used for medicine, for science, for the careful exploration of the fundamental laws of nature. The starships remain in the books. There is something restful in thinking about all of this, the long, slow accumulation of understanding, the way that a question first asked in 1928 by a quiet man writing equations alone in a Cambridge room has slowly unfolded over nearly a century into experiments at facilities filling many acres, into satellites watching the galactic center, into routine medical procedures in every major hospital. The story of antimatter is, in a sense, the story of how a strange mathematical hint becomes part of the ordinary furniture of the world. Dirac wrote his equation, and within a few years, a positron appeared in a photograph. The positron, within decades, was used to peer inside human bodies and find cancers before they showed any other symptoms. The same particle, in greater numbers, is now held in vacuum chambers for years at a time, and compared, atom by atom, to the ordinary matter we are made of, and the answers that come back say, quietly, that the symmetry between the two is, as far as we can measure, exact. It is worth lingering a moment on what this means. For nearly a century, physicists have looked for some difference between matter and antimatter, some asymmetry that would explain why the universe is made of one and not the other. They have looked at the masses. They have looked at the charges. They have looked at the magnetic moments. They have looked at the energy levels of antihydrogen. They have looked at the gravitational acceleration. They have looked at the decays of mesons and the oscillations of kaons. Everywhere they look, they find that matter and antimatter behave as the equations predict. They are perfect mirrors of each other, except for the tiny asymmetry that shows up in the weak nuclear force, which is not nearly large enough to explain the cosmological imbalance. This is a strange situation. The universe must have, at some point, distinguished between matter and antimatter strongly enough to produce the imbalance we see. But when we look at matter and antimatter today, we find that they are nearly indistinguishable. The asymmetry, if it exists, is hiding, either in a process that operated only at very high energies in the early universe, which is no longer accessible to us, or in physics that we have not yet discovered, or in some subtle effect that requires more precision to detect than we yet have. The matter-antimatter asymmetry is, in this sense, one of the open invitations of modern physics. The universe is telling us that there is more to know, and the laboratories that hold antihydrogen for 15 minutes, and the satellites that map the gamma rays from the galactic center, and the accelerators that smash protons together and look for new sources of CP violation, are all, in different ways, trying to listen carefully to what the universe is whispering. There is something soothing about a question that has remained open for so long. We tend to assume, in everyday life, that questions get answered and then move on. The questions of physics often do not work this way. Some of them are answered. Some of them open up further. The question of why the universe is made of matter has been with us for nearly 70 years now, since the first careful analyses of the matter-antimatter asymmetry in the late 1950s. It will likely be with us for some time yet. The universe is in no hurry to reveal its secrets. There is no deadline. We can sit with the question, watch, and listen. Let us drift back briefly to the antihydrogen experiments, because there is something quite beautiful about what they are actually doing, and it bears slow consideration. When the alpha collaboration at CERN traps an antihydrogen atom, what they have managed to do is build, in their apparatus, a thing that has never existed before in this part of the universe at this time, an atom of antimatter, sitting in a vacuum chamber, surrounded by ordinary matter, separated from that matter only by a vacuum and by magnetic fields that hold the antimatter in place. The antihydrogen atom, if undisturbed, would look exactly like an ordinary hydrogen atom from a distance. It has the same mass, the same internal structure, the same energy levels, the same response to electromagnetic fields. The only way you could tell it apart from a hydrogen atom is by what happens when you bring it into contact with ordinary matter. Then it vanishes. The collaboration shines lasers on these trapped antihydrogen atoms. They watch how the atoms absorb light at specific frequencies, just as ordinary hydrogen does. They have measured the frequency of one particular transition, called the 1s to 2s transition, in antihydrogen, and they have compared it to the corresponding transition in ordinary hydrogen, which is one of the most precisely measured frequencies in all of physics. The two frequencies agree to the precision of the measurement to better than 1 part in a trillion. As more atoms are accumulated and measurements are refined, the precision improves. The mirror remains perfect. There is, for many physicists, a quiet hope that one day a difference will be found. Some tiny gap, some minute discrepancy, that points the way toward the missing physics. The fact that none has been found yet, despite extraordinary precision, is itself informative. It tells us that whatever broke the symmetry in the early universe must have left, in the present day, only the faintest of fingerprints. The fingerprints, if they exist, are smaller than 1 part in a trillion. They may be much smaller. They may, conceivably, not exist in the kinds of measurements we are currently making at all, and may require entirely different experiments to find. The patience required for this kind of physics is itself something to admire. The alpha collaboration has been running for nearly 2 decades now. Each experimental session involves the production of relatively few antihydrogen atoms, the careful trapping of them, the measurement of their properties, and the comparison with ordinary hydrogen. The data accumulate slowly. The improvements in precision come one by one, each requiring months or years of work. The physicists who do this work will, in many cases, devote their entire careers to it, and may not live to see the question of matter-antimatter asymmetry definitively resolved. The question may outlast them. It may, in fact, outlast all of us. The universe has been patient for billions of years. We are still relative newcomers to the question. Let us step back and try to take in the whole picture for a moment. The universe, as best we can tell, is roughly 14 billion years old. For nearly its entire history, it has been a universe of matter. There are some traces of antimatter, here and there, in cosmic rays, in radioactive decays, in the cores of stars, in the inner regions of galaxies. But these traces are small. By far, the dominant content of the visible universe is ordinary matter, of the kind that makes up stars and planets and people and books, and the chairs and beds where you might be lying now. And yet, at the very beginning, the universe was different. In the first fraction of a second after the Big Bang, when temperatures were so high that protons and antiprotons could be freely created and destroyed by collisions of pure energy, the universe contained roughly equal amounts of matter and antimatter. For every billion antiparticles, there were 1,000,000,001 particles. The difference, that 1 part in a billion, was the asymmetry. As the universe cooled and expanded, the matter and antimatter began to annihilate each other in vast numbers. For each pair that annihilated, 2 photons flew off into space. By the time the annihilation was complete, the universe was filled with these photons, the cosmic background of light that has been streaming through space ever since. And in the wake of the annihilation, only the slight excess of matter remained. That excess is everything. every star you have ever seen, every planet that orbits any of those stars, every atom in every body of every living thing on Earth, and on every other inhabited world if there are any, is composed of the particles that survived because they had no antiparticle to vanish with. We are, all of us, the survivors of a great cosmic cancellation. The universe nearly destroyed itself in those first moments. What we have, what we are, is the small remainder. There is something quietly humbling about this. The matter that made you up was, at the time of its creation, balanced on the edge between existing and not existing. The asymmetry had been a little different, or had gone the other way. The universe would either be empty, filled only with photons, or it would be made of antimatter. There would be antistars and antiplanets, and presumably antibeings, who would call their matter ordinary and ours strange. The reasons that things went one way rather than the other are buried deep in the early universe, in physics that we have not yet fully understood. For all the strangeness of antimatter, then, perhaps the strangest fact is the one we tend not to notice. The matter that makes us is not the only kind that the universe could have produced. We are not the default. We are, in a quite literal sense, the lucky residue of a cosmic process that almost wiped itself out before it began. And the photons from that ancient annihilation are still here. The cosmic microwave background, the faint radiation that fills the universe, is, in some sense, the light from that great early cancellation. The wavelengths have stretched as the universe has expanded. The photons are now in the microwave part of the spectrum, very cold, just a few degrees above absolute zero. But they are the same photons that were produced when matter and antimatter met each other in the early universe and annihilated. They are the radiation of all those cancellations, traveling outward, filling space. We can detect them. Radio telescopes have mapped them in extraordinary detail. They are, in a sense, the sound of the early universe's matter-antimatter encounter, recorded forever in the geometry of space. There is, then, an old light in the sky, older than the stars, older than the galaxies, older than any matter that has organized itself into anything. It is the light of annihilation, the light of the universe's early near-destruction. It surrounds us now, in this room, in any room. We are, at this moment, being passed through by photons that were created when the universe was less than a second old. They have been traveling for 14 billion years. They are everywhere. They are, in their faint way, the constant companion of everything that exists. Let us drift now, slowly, toward the close. There is no rush. The story has been told in its main outlines. The history of how antimatter was predicted and discovered. The physics of how it is made and held. The natural sources of antimatter in the universe, from radioactive decay to the galactic center. The mystery of the matter-antimatter asymmetry, and the patient experiments that continue to search for its source. The strange interpretations, like Feynman's electrons moving backward through time, hint at deeper symmetries in the equations of physics. The practical uses are in medicine and research. The speculative futures in interstellar travel that may or may not ever come to pass. Here is more to say, of course. There is always more to say about a topic as deep as this. We have not spoken much about the antineutrinos, the antimatter partners of the neutrinos, which are produced in huge numbers by the sun, and which pass through the Earth in unfathomable quantities every second, almost never interacting with anything. We have not spoken much about the kaons and the bemesons, and the many other particles, whose CP-violating decays are studied at facilities around the world. We have not spoken much about the deep, open questions, like whether the neutrinos themselves are their own antiparticles. a possibility called Majorana neutrinos, which is one of the candidates for explaining the matter-antimatter asymmetry through leptogenesis. We have not spoken much about the strong CP problem, which is the question of why the strong nuclear force does not exhibit CP violation in the way the equations would naively allow. These are all stories of their own. They are being investigated by experiments around the world. The deepest of these experiments, in some cases, are running deep underground in old mines, where the rock above provides shielding from the cosmic ray background, in the South Dakota mountains, in Italy's Gran Sasso, in Japan's Kamioka mine, in Canada's SNOLAB. Large detectors filled with ultrapure liquid or ultrapure crystals sit silently, waiting for the rare interactions of neutrinos, or for the still rarer possibility of a process called neutrinoless double beta decay, which, if observed, would prove that the neutrino is its own antiparticle and would open a new chapter in the matter-antimatter story. But these are stories for other nights. We have spent long enough on the main thread. The history is in place. The physics has been outlined. The mysteries have been named. What remains is to sit with the picture for a while before letting it go. Antimatter, in the simplest description, is the mirror of matter. Every particle has a partner. The electron has the positron. The proton has the antiproton. The neutron has the antineutron. The quarks have the antiquarks. The neutrinos have the antineutrinos. For every kind of matter particle, there is a corresponding kind of antimatter particle, identical in mass, identical in spin, identical in the sizes of all its various quantum properties, but opposite in the signs of its electric charge and certain other quantum numbers. When particle and antiparticle meet, they vanish, and their mass energy is converted into other forms, usually photons. The basic facts are simple. The implications are profound. There are some particles that have no antiparticle, in the sense that they are their own antiparticle. The photon, the carrier of the electromagnetic force, is one of these. The photon's antiparticle is just another photon, indistinguishable from the original. The same is true for some other neutral bosons. For these particles, the symmetry between matter and antimatter is trivial. There is no mirror. The particle is its own reflection. For the quarks and leptons, the particles that make up ordinary matter, the antiparticles are genuinely different. They have opposite electric charge, opposite baryon or lepton number, and opposite values of various other quantum properties. They are, in every measurable way, the mirror image of the matter particles. They behave the same under the electromagnetic force, the same under the strong nuclear force, the same under gravity, but in some subtle ways differently under the weak nuclear force. That subtle difference is the CP violation that Cronin and Fitch first observed in kaons in 1964. It is, so far, the only known asymmetry between matter and antimatter. And as we have said, it is too small to explain the universe we live in. The neutrinos in this picture occupy a curious intermediate place. The neutrinos are the lightest of the matter particles, almost massless. They are electrically neutral. They interact only through the weak force and gravity, so they pass through ordinary matter almost as if it were not there. The Sun produces vast quantities of neutrinos in its core, and those neutrinos stream out into space at very nearly the speed of light. Every second, roughly 60 billion solar neutrinos pass through every square centimeter of the Earth's surface that faces the Sun. They pass through your body. They pass through the Earth. They pass through everything with hardly any interactions at all. The neutrinos, in their quiet way, are the most numerous matter particles in the universe. Whether neutrinos are different from antineutrinos is, surprisingly, an open question. The two kinds of particles have opposite values of a quantity called lepton number, and they appear to behave differently in weak interactions. But because neutrinos are electrically neutral, and their other distinguishing features are subtle, it is possible that the neutrino and antineutrino are actually the same particle, distinguished only by their direction of spin. This possibility was suggested by the Italian physicist Majorana in the 1930s, and a neutrino that is its own antiparticle is called a Majorana neutrino. Whether neutrinos are Majorana particles or not is the subject of ongoing experimental searches. If they are, this could be the key to explaining the matter-antimatter asymmetry through processes that occurred in the very early universes. Is one of the things being looked for in the deep underground laboratories. The experiments search for a process called neutrinoless double beta decay, in which a nucleus emits 2 electrons but no antineutrinos. If this process occurs, even very rarely, it would prove that the neutrino is its own antiparticle. So far, the process has not been observed. The limits on how often it can happen have been pushed lower and lower over the years. Future experiments will push them further. The answer, if it comes, may take decades to arrive. There is something fitting, somehow, about the way these experiments work. Patient, quiet, far from the surface of the world in the cold dark of deep rock. Detectors that sit for years, watching for events that may or may not ever occur. The pace is glacial. The rewards, when they come, are profound. Each year of running adds slightly to our knowledge. Each decade brings a new generation of detectors, with new precision, asking the same questions in different ways. The universe is in no hurry to answer. The physicists, by necessity, are not in a hurry either. Let us turn gently to the slow ending of this thread. The universe, as we have said, will continue. The slow rain of gamma rays from the galactic center will continue. The faint cosmic background of photons, the relic of the early annihilation, will continue. The deep underground detectors, waiting in the cold dark, will continue. The particle accelerators at CERN, at Fermilab, and at facilities around the world will continue to produce small numbers of antiparticles for careful study. The penning traps will continue to hold their precious cargo of antiprotons, suspended in fields of invisible force, never touching anything. Some of those antiprotons will still be there many years from now, held in the same fields, having spent decades drifting in their magnetic confinement, unchanged. We have made, over the past century, a strange and delicate kind of progress. We have learned that the universe contains an entire mirror world of antiparticles, hidden in plain sight, predicted by an equation, discovered in photographs of cosmic rays, made in accelerators, held in traps, studied in laboratories. We have learned that this mirror world is, as far as we can tell, almost perfectly symmetrical with our own. We have learned that the symmetry must have been broken, very slightly, at the beginning, in order for there to be any matter left at all. We have learned that we are made of survivors. Particles that, for some reason we do not yet understand, came through the early universe without finding antiparticles to vanish with. The reasons remain hidden, somewhere in physics beyond the standard model, or in conditions of the early universe that we have not yet been able to recreate. But the question is being worked on, slowly, patiently, in laboratories around the world, by people whose names few of us will ever know. There is something restful about this. The work goes on, whether or not we are watching. The experiments run. The data accumulate. The understanding deepens very slowly. In 100 years, we will know more than we do now. In 1,000 years, We may know what the answer is to the asymmetry question, or we may still be asking. The universe is in no hurry. The deep questions take their time. In the meantime, the matter we are made of continues its slow business of being matter. The atoms in our bodies, every one of them, are particles that survived the early annihilation. They were not annihilated then. They have lasted in some form or other for nearly 14 billion years. They have been incorporated into stars and into planets, into rocks and into seas, and finally, briefly, into us. They will go on being incorporated into other things long after us. They are the lasting survivors of a cosmic process whose outcome was uncertain at its beginning. We carry them in us as a kind of inheritance. They are very old. They have been through a great deal. The same is true of every star in the sky. The same is true of every galaxy. The same is true of the dust that floats through interstellar space. All of it, every bit, survivors of an early cancellation that left only the slightest residue of one kind of particle over the other. The universe is built from that residue. It is a quiet thought. It does not have the urgency of most thoughts. It simply sits there in the background of everything, true whether we attend to it or not. We are leftovers. We are what was not annihilated. Let us drift now, more slowly, toward the end, somewhere in Switzerland, beneath a small section of countryside on the border between France and Switzerland. The antiproton decelerator is humming through its slow nightly work. Protons enter at high energy. Antiprotons are produced in a target. Some of them are captured. They are slowed down, very gradually, by techniques that took decades to develop. By the end of the process, they are moving slowly enough to be loaded into the small traps where the experiments will study them. The whole apparatus runs through the day and into the night. The physicists, working in shifts, watch their data accumulate. Each shift adds a little to what is known. In the antihydrogen experiments, the antiprotons are mixed with positrons, and small numbers of antihydrogen atoms are formed. The atoms are trapped in carefully shaped magnetic fields, where they remain neutral and quiet for as long as the fields can hold them. Lasers are tuned to particular frequencies. The atoms are illuminated. Sometimes the atoms absorb the light and then re-emit it. The patterns of absorption and emission are recorded. Comparisons are made with the corresponding patterns in ordinary hydrogen. The two patterns, so far, agree. In the gravity experiments, the antihydrogen atoms are released from their trap, and where they go is observed. They fall. They fall in the direction of the Earth's center, the way ordinary matter falls. The acceleration, within the precision of the measurement, matches the familiar 9.8 meters per second of ordinary gravity. Antimatter, it appears, is no different in this respect from matter. It feels the pull of the Earth, just as we do. In the precision experiments, the antiprotons are studied in their penning traps for months at a time. Their charge-to-mass ratios are measured. Their magnetic moments are compared with those of protons. Every comparison, so far, supports the prediction that matter and antimatter are identical, except for the signs of their charges. The mirror remains perfect to the precision we can currently achieve. The work of measurement and comparison will continue. There is no obvious endpoint. As long as physicists can devise more precise experiments, they will run them. As long as the answers continue to agree with the predictions, the precision will continue to be pushed further. One day, perhaps, a discrepancy will be found. A small gap, some difference between the way matter and antimatter behave that the equations do not currently predict. If that happens, it will be the start of a new chapter in physics. But for now, the chapter is still being written. The data continue to accumulate. The instruments continue to improve. The questions remain open. Above the laboratories, the sky is filled with the same old light it has always had. The sun, made of ordinary matter, continues to burn through its nuclear fuel, occasionally producing small bursts of positrons in its core. Cosmic rays continue to fall onto the Earth, occasionally bearing antiparticles produced in collisions far out in the galaxy. The galactic center continues, quietly, to glow at 511,000 electron volts, the soft signature of electron-positron annihilation. The cosmic microwave background continues to fill all of space, the relic of the early annihilation, the photons of the matter-antimatter encounter that happened when the universe was less than a second old. All of this is going on, all at once, all the time. The universe is, in its quiet way, a place where matter and antimatter are continuously meeting, converting, and transforming. The conversions are mostly small, the transformations are mostly local, but they are happening everywhere, all the time. The faint glow of the galactic center, the brief positrons of the banana on the counter, the trace antimatter in cosmic rays, the annihilations in the PET scanners of every major hospital, the careful experiments at CERN, the single particles held in penning traps for over a year, suspended in a vacuum, never touching anything. Antimatter, in its way, is not exotic. It is part of the ordinary fabric of the universe. It is just rare. Rare enough that we had to predict it before we found it. Rare enough that we have only ever made tiny quantities of it. Rare enough that, in our daily lives, we never encounter it directly. But it is there. It is in the equations. It is in the cosmic rays. It is in the gamma rays from the galactic center. It is in trace amounts, in our own bodies, in every banana, in every isotope that decays by positron emission. And the universe, in its patient way, continues to produce it and destroy it, and produce it and destroy it in countless small encounters across the vast distances of space. We see only a fraction of what is happening. We have built our small instruments and pointed them at the sky, and the sky has whispered back to us, in faint gamma rays and in subtle asymmetries, that the story is more complicated than it first appeared. The whisper is enough to know that the universe is, in its bones, a more symmetric place than it looks. The matter and antimatter, deep down, are nearly the same thing. They are different excitations of the same fields. They are mirror images of each other. The mirror, at the smallest scales, is almost perfect. The asymmetry, that small wrinkle that gave us a universe of matter rather than nothing, is so small that we are still hunting for its source, and so we drift toward sleep with this thought. The universe we live in is built on a small asymmetry whose origin we do not yet understand. That we are, all of us, the descendants of survivors. That somewhere in the laws of physics is a tilt, an imbalance, a tiny preference for matter over antimatter, and that this preference, ancient and unexplained, is the reason any of us are here at all. The mirror remains almost perfect. The asymmetry remains very small. The questions remain very deep. The work goes on. The universe continues. The stars continue. The galactic center continues to glow softly at 511 keV. A slow rain of gamma rays from countless annihilations, a faint signal of an old process that has nothing to do with us, that will continue long after we are gone. There is nothing more to do here. There is nowhere to be. The mirror world of antiparticles is, at this moment, behaving exactly as the equations predict. The matter world is, at this moment, slowly going about its business. Somewhere in the careful laboratories, antihydrogen atoms are being trapped and studied. Somewhere in the deep underground detectors, Large volumes of pure material are waiting for the rare events that may or may not ever come, somewhere very far above us. The cosmic microwave background continues to fill all of space, photons from the old annihilation, traveling onward and onward. The universe is in no hurry. The work, on its own scale, is going perfectly well. There is nothing here that needs to be rushed. The questions will be answered when they are answered, or they will remain open. And either way, the photons will continue to travel. The antiparticles will continue to be made and destroyed in small quantities. And the great patient mirror at the bottom of physics will continue to reflect. And the stars will continue to shine, made of matter that survived the great cancellation, made of particles that, by the slimmest of margins, were not annihilated. The stars do not know this. They simply burn. They are made of what is left. And what is left, in the end, is what we are. There is nothing more to be said about it just now. The night is long. The mirror is patient. The universe has been doing this for a long time and will continue to do it for a long time more. The questions are deep. The answers are slow. There is no need to stay awake for them. The galactic center continues to glow softly. The antihydrogen atoms continue to sit in their magnetic traps. The cosmic background of photons continues to fill all of space. The universe, in its quiet way, will still be turning when we wake.